Yeah, so thanks everybody to the very exciting second lecture on post-quantum cryptography. What we did last week is take me 1 minute to recap, right? So I gave this introduction to post-quantum cryptography and the big lessons learned. Post-quantum cryptography has nothing to do with quantum computing, right? These are just new public key schemes that hopefully cannot be attacked by quantum computers, which don't exist yet. And then we honed in on one specific one. There's 3 or 4 families that are standardized and slowly rolled out. You know, they're the first application using them, web browsers and so forth. And what we did is, out of the 3 schemes that are really prominent, we picked hash-based, frankly, because they're really nice to teach and it's kind of a nice, gentle introduction. And the one that's a basic building block for all the hash-based signature schemes that are out there is so-called the Winternitz one-time signature, right? We did them very nice. It was kind of messy, but I hope everybody survived the homework assignments and stuff. Does anyone remember what was the big drawback at the end of this Winternitz one-time signature? What is the big limitation? Why is there kind of a pain in the neck? Does anyone remember? It's in the name. Any ideas? Yep. You can use the key only once. This is stupid, right? Who has used a one-time pad? You know, this was lecture 2 in October. Who used the one-time pad ever to encrypt an email or WhatsApp message? I'm kidding, nobody, right? One-time pads are stupid, and they're kind of in the basic form stupid, right? So, and now very exciting, we get much, much closer to the real-world employment. Namely, we find a way to use the Winternitz one-time signatures, but even though we might have 1 million Winternitz schemes, we only have one public key. This is great. This is the topic of today. It's in terms of material somewhat less than last week. So today we're going to talk the principle about the Merkle, Ralph Merkle signature scheme. Then we do Merkle signature scheme of degree 3, and as a third topic we generalize. So essentially we talk about one topic, which is better than last week. Essentially we introduced 2 schemes and PQC, so it's and I really like that. Okay, so first chapter for today is the principle of Merkle, right? Signature schemes, or MSS, mostly abbreviated MSS in the literature. Okay, so, AKA, also known as the different names out there, right? They're sometimes called Merkle trees, Merkle-Bäume, right? Merkle trees, or hash trees, and a little bit motivation, you know, to prevent you a little bit more from falling asleep. They have application beyond this very specific post-quantum signature schemes. So hash trees are very general constructions. They're used in different parts of cryptography, and particularly the people that are studying IT security. Here you probably encounter in some of the advanced lectures, you're probably going to deal with hash trees again. So, right, so maybe an additional motivation, okay? So that was invented, they were invented by Ralph Merkle in 1989, so about 12 years after public key cryptography was invented. Who's heard the name Ralph Merkle before? I don't know whether I introduced that in the lecture, but in the book. And anybody heard the name before? Yeah? And what is, do you remember the context in which you heard about him? Yeah? No. Good guess. Maybe too.
Yesterday I was a bit outraged that you could only use them once, the signatures. So basically, then I stumbled upon the name Merkle trees and how they use.
Yeah. So they're definitely used for Merkle trees. It was a good guess with Simon. No, he's actually one of the co-inventor of public key cryptography, right? So there was actually, I think, Diffie-Hellman, Whitfield Diffie. I think it was him. He said we shouldn't call that Diffie-Hellman, right? They normally credited for inventing public key, but he said it should be Diffie-Hellman Merkle, right? So he's one of the co-inventors, but they worked independently. So it's one of these people that didn't get the credit they deserved, right? So great guy. Okay, so and here is I start with a very high level view on. This is a very simple diagram I'm showing, just to essentially the goal where we're going to, right? So this is this big box, right? This is our MSS algorithm. So that's essentially the topic of today, right? What we're going to do. So what we have to do here, if you want to sign, you pre-compute 2 to the t signature keys, right? Keys. Meaning, so you have k private, comma 0, and k public, comma 0. And this is time travel. So we're back to the last lecture 2 weeks ago, right? So this is blah, 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 blah. And you do that 2 to the t times up to k private index 2 to the t minus 1. Yeah. 2 to the t minus 1 and k public, comma t to the t minus 1. Very messy, right? And then a big cool thing is, even though, and t can be large, we're going to talk about it, right? This is exponential, right? Even for, t equal 20, this is going to be a big number, right? What you get out, and this is only one public, okay? So, and this is, so all of these are 2 to the t Winternetz OTS. So this is the homework you did last night, right? Where you worked on this is the last Übungszettel, right? The last homework assignment. This is nothing different from what you do. So we still need that urgently. You do a lot of them, you pre-compute, but somehow these might be 1 million here, right? Somehow we manage to link those 1 million keys, I'm making up a number, to one single public key, which is much, much nicer. So actually the big problem with this one-timeness is not so much generating them. Does anyone recall how do we compute the public key here? What is the main operation we have to do with the Winternetz? Yeah.
Using the same function over and over.
Yeah, and what is the function?
That function.
Yeah, and what is that in practice? Yeah, a hash function, right? It's very good. Use a function over and over again, and a S for hash functions, because hash functions are designed to be fast, right? So what I'm trying to say, computing 1 is no big deal, but even computing 1 million is no big deal, right? I mean, I'm making up a number that might, even for if this is 1 million here, that might take you in practice seconds. And you only have to do it every few years, right? This is not a hype. So generating them, which is inherent in this one-timeness, is not the problem. The problem is if you want to push out 1 million public keys, right? And they may be stateful, blah, 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 blah. So the big step is, can we go from here to here? That's today's lecture, okay? Okay, yeah. And so maybe I give an example here. So example is, let's say you want to do 10 to the 6 signatures in 2 years. It's totally random, right? But it also helps me, right? When I prepared that, when I wrote the book, so what does it mean? What is T? And then you do some numbers, right? So any idea? So you say, let's say in practice, I would probably want to sign about 500,000, 500,000 signatures. And now to make safe, you really have enough. You say, okay, I prepare something like 1 million. Does anyone know out of your head what would t be? What do I have to choose with t here? Which number do I need for t here? 2 to the 20, right? 2 to the 20 is 1 mega, right? 1 mega is roughly 1 million, right? 1 kilo is roughly 1,000, right? So if you want to do that, you choose t equal 20, since 2 to the 20 is larger than, this is one, you use your smartphone, right? Punch in 2 to the 20, it's 1 million, blah, 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 right? So what I'm trying to, t is moderate, which is good, because later on the computational complexity for this is proportional to t. Proportional to 1 million might hurt you. Proportionally to 20 is probably no big deal. That's what I'm trying to see here, right? It's exponential. Good. So if you're still awake, this is already good for you. Okay, so now which blackboard do I'm using this blackboard? Okay, so very simple example just to believe me what like the basic mechanism behind it, right? We start with a toy example, baby example, right? T equals 1, right? It's very unexciting, right? The first thing is kind of what you see on the left-hand side, what's inside this funny box, right? So we have to pre-compute signature pairs. And by the way, in the book, and you can take notes whatever you want, in the book I'm using uppercase for X and Y, right? Großbuchstaben. You can use small, it doesn't matter, right? But just to warn you, and because you don't really see that on the blackboards that well. So, I'm following this very uncomplicated. If t is 1, right, 2 to the 1 is 2, 2 minus 1 is 1, so you have 2 key pairs here, right? Very unexciting. Okay, so, and again, just to reiterate, these are 2, by now, because you did your homework assignment, right, very boring, right? Stuff from last week. We do exactly what we discussed last week, right? So, and now when you see what are the 2 alternative names? Merkle trees or hash trees. Now we're computing a tree. And the tree is so ridiculous easy that you almost don't know what Christof is talking about, okay? So the tree, and this is because t is so small, so the tree looks really stupid, right? Stupidly simple. So what you do, you always start in the bottom. This is going to come up a few times today. So you start with you just computed that with your laptop or your iPhone, right? And then you hash the public key, because in the end, what you want to, somehow you want to deal with the public keys, right? And we're going to talk about that a lot. So you use the hashed version of the public key. Oh, what am I doing here? I'm missing an H here, right? This is H of, and also here, this is H of. Okay. Is that computationally hard? No. Hash functions are very, very fast, right? They're designed to hash 1 gigabyte hard disk, whatever, right? And here we talk about a few hundred bits. So this is lightning fast. It doesn't look like a tree. Now comes a tree, and again, the tree is absurdly simple. You just have one branch here, and up here, what you do, you take the 2, they call it leaves, you take A0 and A1, you hash them again together. A0. Does anybody know what this symbol means? Yeah. Concatenate. Concatenate Verkettung. So that's a fancy word for putting it right next to each other, right? So this is A0 concatenated with A1. And This is miraculously, wunderbarerweise, this is a public key. Okay. And now we have to see. Now we have to show you why that works. Why does this work? Okay, let me see where I'm going to place it now. That should be. I should be able to pull that off. So let's see. So let's see. Right now, you don't know why that works, right? Let's look at the protocol. So we have, our actors, Alice and Bob. Alice actually does exactly what we've showed here. That means she computes h of A0, A1, sends it over, and Bob knows public. Okay. This is kind of what we expect, right? You can still be asleep for not for much longer, right? Soon we're going to talk about this one crucial aspect of not the one, but the first crucial aspect of this lecture. So Alice, oh yeah, maybe I should have said, what do you think with this setup? How many messages can Alice sign with this here? What do you guess? Any guesses, yeah? No? Yeah. 2, exactly. Right, so we do 2 here, right? 2 is no big help, but maybe if you can do 2 later on, the next thing, actually the main part of the lecture, we're going to how to sign 8 messages. Things become more complex, and which is t = 3. And once you believe me that, we go to the general case. But we start with something very simple, right? And I'm glad I asked that because it's clear to me because I did the lecture notes, but it's easy to get lost. So that's why I asked. So we talk about the M0 is the first out of 2 messages, right? So the first thing that Alice does is she computes a signature, which we call S0, right? Very reasonable name, right? Message M0, signature value. With a signature algorithm, M0. And what do you think, what kind of key, what kind of value do I have to put here as an index? This is last week. How do you? First of all, what kind of keys are we using for signing? Public key or private key? Whoever gives the wrong answer is going to be kicked out here, yeah? Yeah, you can stay. Okay, private, right? But so what is the private key? These are the X's here. I'm doing that very slowly because I'm teaching it for the first time and I wrote the book. Oh, this is confusing, right? So, and what would you choose, X0 or X1? This is a joke, right here. X0, everything's 0 here, right? So, and later on, for the second message, surprise, surprise, we're going to use X1 at some point, right? But again, this is, if you want to write that down in your notes, this is like the 5th time I'm saying this. This is Winternitz. Very boring by now. Stuff from last week. This is not, we're not talking about the actual signing is what we did last week. Last homework assignment. Okay. And now we do what we did last week. We're sending over the message, M0, the signature we just computed. And then which other value with the Winternitz scheme, what else does Alice has to send over here? Yeah? Checksum, right, okay. Yeah, no, but we're skipping that because this is absolutely the right answer, because this is specific to Winternitz. There are other schemes out there, but basically, I'll give you the answer, because maybe my question is not great. Why 0? You're sending the public key, right? You're sending the public key, this is kind of what works. And do me a favor, so I'm spoiling my nice pedagogical trick here. This is not going to work this way. We have to do something. We have to later on add something. So keep, drei Kästchen, right? If you have graph paper, 3 little graph units, is that here, right? So what Bob has to do, Bob wants to verify. And the big question here is, is Y0 authentic? What does authentic means? Y0, where is it? Is a public key. Is this really Alice's public key? There was a question last week, actually, that came out twice in super questions out of the audience by you guys. And they assumed, so what happens if Oscar replaces his public key? But this is outside the attacker model, right? Now we assume the keys are distributed correctly. It means a public key. That means Bob knows this is really Alice, and Bob knows that. If he drops that assumption, the whole thing is unsecure, right? That we assume that, and I mentioned about that's the last lecture of this semester. I think in 3 or 4 weeks we're going to talk about that. Right now, and this is the first time, please wake up, stop Insta, okay? Bob knows K-public, and so public knows this, Bob knows K-public is really coming from Alice, right? What he needs to know is Y0 coming from Alice, right? So now we're looking at this hash tree. It's more like a hash treechen, right? Little Q tree here, right? So means he wants to know, is this value correct? He has this value. He only has this value, right? So what, and let's see, what can Bob do? Bob is watching a video. Bob goes to Wikipedia and look at the Merkle trees. Y0, so which step, which computation can he do with Y0 that's here on the blackboard? Yeah? He can hash it, he can compute this here, right? This is good. That means he gets up to here. This is nice. Is this enough to recompute K-public? No. What is missing? What would he like to know here? What's missing? Yeah, you? Exactly. Y1, right? He can do Y1, but then the problem is really good. What is the problem if, so one possibility, and don't copy, you're going to die if you copy, right? So you're not dying, right? This would be one way out. What would be the problem of that if he does that, if he do that here? What could Oscar do? Because Oscar would see Y1. What could Oscar do with that then? It's actually not it's a bad question. Drop. It's still, he would give his public key away, which is no big deal, but we don't want to do that, right? What we do instead, we give A1 out here. Okay, so that's what I want to say. Okay, so, and this is so exciting. I mean, as I assume most people can follow, for these small parameters, t equal 1, it's not super exciting. So I put that in red parentheses. Later on, this red part is going to be longer. Okay, just to spoil my nice lecture here. Okay, if we do that, so is that a problem? No, because in terms of security, because let's just, for the sake of argument, let's assume Oscar is here. So what Oscar learns is A1, he has this value, but in particular, he cannot go back, he cannot compute Y1. I mean, one wouldn't be of that much help for him, but it's still good. So this is like a low value, right? Wert, mit keinem Wert that you give away here, okay? Now comes the interesting thing, everybody awake now. What does Bob have to do to check whether Y0 is correct now? So Bob has Y0 and he has A1. And he knows that K-public is correct. What does he have to do? If you can answer that, this is 50% of the lecture today. Any question? What kind of computation is to do? And it's not complicated. We're not talking about, this is not Fourier transform or something crazy. Any ideas? One taker, yeah?
He's going to hash
Yeah, exactly. So he very good. Is that what I wrote down? He recomputes A0 by taking whatever SHA-3, you know, which we also did in this course. He computes the SHA-3 version, so to speak, of Y0, right? And there's all kind of public domain implementation of SHA-3 or SHA-2 or whatever hash function you like, right? This is great. So now he's actually here. This value he just got for free from Alice, right? So, and now he does H of A0 concatenated A1, and he checks, you know, this is supposed to be a question mark, Fragezeichen. Is this equal to K public? And K public is, which is somehow, again, this is what we do at the end of the course, magically authenticated, right? So this is what you use certificates for, right? So if correct, that means if this here is correct, this check, right? This is an if statement, right? If this is correct, what does he know? He knows, well, A0 and A1 are correct, meaning, but if A0 is correct, Y0 must be correct. You know, this is this crazy thing with hash functions. Even if one bit would be different, the output of A0 would look totally random, right? So if this check out, this is a very strong statement. If this equality, this check works out, he's assured that he has the correct Y0, right? If correct, Y0 is authentic. Authentic is, and when we talked about security service, authentic is a fancy term. Yes, this is really coming from Alice, right? And now, what does he do then? Well, now he knows he has the correct public key, and now he verifies, for instance, Winternet's one-time signature scheme. So he is now running Winternet's with the Y1 he just computed. No, Y0. Is that right? Yeah, Y0. And the inputs are S0 and M0. And the outcome of that, and now we're back to good old digital signatures, yes or no, right? Digital signature is valid or no, right? So, okay. So who could, little vote, who could roughly follow what I'm telling you here? Who think I understood 80%? Okay, so that's pretty good. 80% understood 80%. No, it was almost 100. You're great. You're great. You're too smart. Okay. Wir liegen gut in der Zeit. We're doing really well here. So now I'm just going to show you, this was message 1. So what I'm going to do here is, you just follow, you write underneath, right? You don't have to switch. Yeah, Frage. Ja, gute Frage. Good question. So the question is, I'm still sending public key to Bob, right? But what is the difference from the naive if you, this is a super good question. Maybe let's, for large T, how would you naively use Winternet's if it weren't for the Merkle scheme? This would be the same, right? And when do you have to send them over, these keys here? In practice, what would you do? Yeah.
At the beginning, the first step, you will usually send over all of the keys to bridge it from
Yeah. Originally, you have to send them over at this point here. And sending over, you're right, a kind of in bandwidth, the same thing, right? But they all have to be authenticated. Good luck, right? So the one high-value, complicated transfer, this is a super question. All the others didn't care about that, right? this is hard because I think I asked it last time, who heard about certificates on the internet? Everybody, right? Use certificates. So they are pain to do. They're really complicated. There's all kind of drawbacks, computational, blah, blah, blah involved here. You only do that once, right? This is the invention. It's a very good question. And the other thing, if you go back to your suggestion, so even if you do that, who is getting those? Everybody wants to talk to you. So you not only have 1 million, 2 to the 20 keys, for instance, that have to be authenticated, all other children have to get them, right? And here, everybody gets a public key, what we do anyway, right? But it's a very good question, right? Yeah. So it seems almost the same to do it the other ways, but then in practice, when man sich das durchspielt, right? If you go through your head with that setup, it's become really messy. Very good question. Any other questions? Very good. So what I wanted to do, I want to show you how to deal from here with the second message. Okay, the second message we do now again, Alice. So I'm continuing, I'm extending that blackboard, right? Alice. So Bob already has kpublic. Now Alice has message M1, which is really the second message she wants to sign. She computes again the signature with her favorite signature algorithm, which is probably Winternitz, using X1. Now she sends over M1, S1. She also has to send over the public key that belongs to X1, which is, surprise, Y1. An Eck. Oh yeah, I'm going to change that. This is not Bob, this is Charlie. This is a different person, because then it becomes a little bit more interesting. So now Charlie has again the question, so Charlie knows, okay, public, this is a better setup for it. Again, I'm teaching this for the first time, right? I make beginner mistakes. Okay, public, so different recipient. So what he, again, doesn't know, Y1, from Alice. Fancy terms, is Y1 authentic from Alice, right? Is this really coming from Alice? He only knows kpublic, right? What he does know, because he looked in my book on Wikipedia, he knows this is a construction principle behind that, right? Right. So which additional, so Charlie wants to link Y1 with kpublic, right? So what can he easily compute given Y1? Which other value can he compute here? Yeah. A1. So he is very easily gets to here, right? What does he need to get to kpublic? What's the missing value? Yeah. A0, right. So in this setting, Alice is sending over A0. And because this is so exciting, we put that in red parentheses. Again, later on, we're going to have t values, and then the parentheses make a little bit more sense here. Yeah, and now, gleiches Spiel, same Spiel as before. Charlie computes A1 by hashing Y1. Now he can hash the concatenation of A0 and A1. And again, now Charlie can also, just like Bob before, check whether this is identical to the public key he knows. Now, if correct, he can use, for instance, Winternitz verification algorithm with Y0 on M1, I call this sequence doesn't matter, S1, M1, and the outcome is true or false. Da-da-da. Okay. Oh, this is maybe also kind of a nice thing to talk about. Is everybody copied here? I'm going to show you, if you haven't copied. Do you have a question? Any questions? This is maybe also good, because your question was really good because we don't have a good feeling about this one-wayness. What do we do? What in practice happens is Alice first sent her first message to Bob because she likes Bob better or whatever. Yeah. Oh, do you have a question? Yeah.
Yeah, I wanted to ask
Yeah.
whether Alice also sends over the indexes, because Bob and Charlie couldn't know
Yeah.
how to do that.
So his question is whether Alice also has to send over the index, which is 0 and 1 here, right? And this is absolutely, yeah, index going to play a big role. Good question. I want to give you a little bit feeling how do we do that in the real world. Here, so first she sent the first signed message to Bob. What she also, after she's done that, she has to put a check mark, meaning I use that up. You know, it's a one-way signatures, right? And then you go there, right? But absolutely, you need the index, otherwise, actually, here it's not clear because it's symmetrical in this binary tree, but in 10 minutes, your question makes sense. Okay, gut. I'll believe you that you may largely understood what I'm talking about. This is the first one. Okay, so this is halbe Miete, right? This is half of the game, half the rent. Okay, second chapter. What does it say? MSS of degree 3. Let's look at that. Okay. So a lot of examples. This is not what the books typically do, right? And the thing is, with the indices, it gets really messy. I mean, if you read the literature, it's not really that complicated. It's much easier in elliptic curves. But you will see, with the trees, it becomes pretty messy, and that's why and Tim Gneisum, and the co-author of the book, and me, we had big discussion, what's a good way of teaching that, right? And we're coming up with this t equals 3, right? Gut. So we're looking for, what we try to do is Merkle tree with t equals 3. That means 2 to the 3 equals 8 signatures. This was t equal 1, was 2 signatures. It didn't even, is it only me? I'm a big city child. This doesn't look much like a tree to me, right? This looks like 2 values and they somehow merge together. Now, in a few minutes, you will see why it's called a tree. Okay, now we're going to have a big Zeichnung, big figure. So I would say you need probably half a page, right? In case his notes, if you're at the end of your whatever thing, turn over, start a fresh page, right? Yeah. So the first thing we do is compute k private, k public. Yeah. Of what? Again, Winternitz, whatever that was, right? If you don't remember, no big deal, just. And we put them at the bottom, right? So this is going to be now a tree structure. So you might need not half a page, but at least 1/3 of your page. If you leave half a page, I think the picture is going to be prettier, which is nice. Okay, so we start with x0, y0. This should be fairly close together, right? We're going to have a lot of values here. So this is Winternitz, right? This is from a true random number generator, and here you hash 8 times or 256 times, something like that. This is with the first one. With the second one is x1, y1. x2, y2, x3, y3. And I'm not going to put all down. I did a lot of Probevorlesung test lectures to myself. This is enough. Oh, no, I'll do more. We have more space than I thought. Okay, so we do x4, y4, x5, y5, x6, y6. And this is all in the book. You don't have note taking. It mentions that if you take notes, it's better to understand. Do you remember this AES drawing I did here, right? Everybody says, why don't you give that out to students? I give that out, right? It's in the book, which is free for you guys. If you do the drawing yourself, you better understand. Surprise, surprise, right? So this, maybe I go back to this here. So we want to, at this, which is barely a tree, right? This is a very pathetic tree, right? So we want to do with the same idea. And what was the first step that we did? We went to here. We computed the A values. And this is what you're going to do now. So you compute A0, which is the hashed version of Y0. You do A1, which is hash of Y1. But here we only do the first 4, okay? Otherwise, I'm running out of chalk here, out of Kreide. Blah, 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 blah. And I think at the end, which one do I need? Yeah, let's stop that here. Okay, and now the same construction principle as before. You take 2 and merge them together because that's a binary tree. You could also do trees where you group 3 together. We're not doing that. We're doing it the easiest, the most natural way. So you move those together. And here in this row, we had the values A, and now we use the next letter in the alphabet, which is B. So we call this B. And any idea, what are we hashing together here? Any ideas? Yeah. A0 concatenated to A1. Exactly what we did, right? It's not rocket science, right? A0. Okay. So we've taken care of those 2 babies, right? The 2 A values on the left-hand side. We have 6 more to go. Any other, what should we do next? Yeah. No, you're good. Concatenate A2 and A3. Let's do the concatenation. Stay with me, don't leave. A2, right? A2, concatenate A3. What's a good name here? B1. Great name, B1. Okay. You get the idea? This becomes B2. And you know what to write here, right? I'll give you 45 seconds to fill this here, right? This is what, right? Do it, right? And then I'll tell you later whether you did it correctly, right? Of course, right? Very nice geometry. And this is why it's good to do that very slowly and do this stupid drawing on the blackboard, because everybody knows what I'm doing. If I could have projected, I get a projector, probably the system was probably 20,000 euros for one year, right? I could have done that. 20% of you guys would know what I'm talking about, right? We do that very slowly. It's logical. It's great. Okay. So, and this actually, we have levels that play a pretty big role. This is level. This is level 0. This is level 1. Yeah, it's level 0. What's the next? What do we do now? Again, the goal is here. What great! We had 1 public key. Right now, we still have 1, 2, 3, 4 public keys. What is the next thing? What can we do? to reduce the numbers of Bs further. Any ideas? You get 10,000 euros, right answer. 1 bonus point. Okay, here. Exactly, see, right? Here, good location, okay. See, which index? Exactly. We take those two and concatenate B0, B0, and B1. And what's a good index for C? Very good. And now, go ahead. Do what's needed here, right? You know what to do, right? This looks so nice, geometrically, so logical, right? I do it myself, too, as well. Okay. We are almost there, right? So what in terms of reduction, right? We started with 8 values, right? This was A0, A1, A0 up to A7 here, right? This was A7. We cut it down to 4. We cut it down by 2, which is, by the way, exponential reduction. This is pretty quick. You don't see it. 8 is not that massive, yeah? I guess so, yeah. This is level 2, and then we have level 3 here. Of course, we're concatenating C0 and C1 with a hash function, which we call D here. D, this is hash of C0 concatenate with C1. This is still good. And now comes this, how great. And what's the difference? What is this also? What we call this also? Yeah, K-public. This is the K-public. It's protected by certificate, blah, 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 blah. So this is the K-public that later on represents Alice's signatures, right? This is put in the web browsers or whatever. This is pushed out, right? Okay, so this is level 3. So these are the... This is stupid, right? 3 should be, there should be 0, 1, 2, 3 in one column. This is not nice what I did here. I do apologize. Okay. So, and now come names. There are only 2 names, right? I use green. You can just continue with whatever you're using. So these original values, the A's, right? A0, 1, 2, up to A7, these are called the AIs are the leaves, the blätter, and D, this is called the root, okay? And I was so upset when I wrote the book, and why are the names really stupid? What is stupid about them? I'm from Cologne, big city kid, right? I grew up without nature, yeah. Yeah, I mean, roots tend to be on the ground, right? You know, next time you're in the forest, right? On vacation, right? Leaves tend to be up. This is upside down, right? And I was actually toying around to draw that the other way around. I mean, first of all, I would be against all literature, and it doesn't work, right? So it's okay. Just I want to, in case you're confused too, me as well, right? Okay, write down. Professor Paar says naming is stupid. Okay. Yeah. No. This is leaves, this is roots, these are intermediate nodes or whatever. Very good question. So really leaves are really only the bottom, at the top are roots. Yeah.
If we send them together, do we also just send M0, S0, Y0, and then A1, B1, C1?
This is what we need to know now. Yeah. This is, now it's getting really, so far, you know, I agree. I mean, maybe, you know, it took me whatever, a long time to do something really simple. The interesting thing is now what do we send over, which was trivial, right? You always sends the other one. This now it's getting interesting. Can write down aufpassen. Okay. So now we try to sign, and we're not starting with x0 because that's not the general case. It's the first one. So we assume Alice already burned x0, x1, y1. X2. So she already signed 3 messages. She wants to sign the 4th message, right? Now let's see what's going to do. If you don't have space on your in your college block, your note-taking journal, just go to the next page. No big deal, right? So we have Alice. We have Bob. She, at some point up here, really, right, before this starts, she has sent kpublic over. So kpublic, and if you want to be exact, has been authenticated. It's really coming from Alice, right? This is always what we assume. So now what Alice wants to sign with x3 is, of course, a message M3, right? M0, M1, M2 have been sent either to Bob or to Charlie or somebody else, right? So now it's message number 4. Where are we? Okay. So first thing she does, for instance, Winternit's one-time signature, she computes the actual signature using uppercase x3 with message M3. And again, I'm repeating myself. Right now, we have not really used Merkle trees, right? This is still stuff from last homework assignment here, right? Now it's getting interesting. Now she's sending over a fairly long message, which consists of M3, S3, of course, Y3. I'm going to switch for a second. Oh, don't close the parentheses. Don't close the comma. I made a mistake, of course, right? So, meaning is she is. No, I'm not using different color yet. So she's sending Y3. With Y3, Bob can compute which value from Y3. Which value? Yeah. Very complicated, right? So A3, that means he is here, right? He is here, right? But he only knows one value that is authenticated to Alice, which is this here, right? Now we have to work our way up. So which other value does she need to get up to this level here? You want to answer? B0 is good. Is that right? Right. Oh no. B0, we need that too, right? But what is the logical first one? Then he doesn't know B1 yet, right? Maybe as yeah. A2, right. B0 was the right answer, was just too early. So, and now we, different color, red. So, so here we call this A2, A2, right? We do A2, and with A2 he can compute B1. Everybody with me? Everybody sees that? Saves me with the push. They're pretty. They're heavier than they look. Okay, those blackboards. And then he has to compute B0. But we make it really easy for him. We send him B0 in clear. So B0 is immediately sent. I'm going to switch blackboard. Oh yeah, here's a nice thing what I'm going to do. So sending A2, sending B0, and now let's jump into the, I'll get to you in a second. Let's slip in the mind of little Bob, right? So what can he do now? He's here already. With A2, he ends up here, right? B0 he has 2, so what can he compute from here? Given B0 and B1, what else can he compute? Yeah, very good. He then means we use a different color. Let's do this. What he computes, we use a different color. I use green, you can use, so A3 he computed, B1 he computed, and as the student just said, now he can also compute C0. So on the left-hand side, it's great, right? So with the, you see what I wrote in red, B0, A2, B0, A2, it's getting up to here, right? So what's missing so that he can compute K public? Very good. So C1, and C1 is not being computed, it's being sent. Send is right. Roter Kringel, red circle, right? So that means the one value missing is C1, right? And this, what I wrote in red, has a very fancy name. That's the authentication path, right? Authentisierungspfad, right? Authentication. So this is the authentication path here, right? This is okay, which is very fundamental, very important part, of course, of Merkle signature schemes. Okay, and now Bob. Oh, maybe this is so. The question is Y3 authentic? And again, authentic is a fancy term for, is this really coming from Alice, right? He does know that key public is really coming from Alice. You had a question before, is that this? Don't spoil. No, spoil is good. I was afraid you were doing that, so that's why I didn't take you. Okay. And now what we have to do is actually, this is trivial by now, right? Yeah. So you see it's can you distinguish between green and white on the blackboard? Yeah. So we do essentially the green circles we write down, right? So this always starts from the bottom. So the first thing that Bob does is he computes A3, right? A3, which is the hashed version of Y3. Then the next one, he's computing B1. You see B1 is also green, right? So he's computing B1, which is the hash over A2, A3. And then he does, we just go up the tree there, C0, C0 is hash of B0, B1. And then at the end, he is computing D is equal to H of C0 concatenated with C1. And here comes this super important, alles Entscheidende, the decisive check. Is this actually public? Same as before. If correct, he can verify. He runs Y3. What did I use? Which S3, M3. And what outcome is either true or false. Gut. War gar nicht so schwer. Wasn't that difficult, was it? So, Zwischenstopp, Spielstopp. Who could follow 80% of what we're talking about? Well, it was close to very good. I'm too slow. No, but it's really, we have like this world famous crypto guy here, a colleague of mine, and I told him, I'm teaching hash chains. He said, really, this is so difficult to explain, right? He's way smarter than I am, right? The thing is, sometimes you have to be slow. No. Julian prepared homework assignments. Don't you worry. Yeah. No. Here's what I mean. I thought originally I wanted to have not an index that's too high, but I still wanted to see the. Yeah. Plus, this is what in the book. Right? In the book, we always thought the third one. It works for all. No, but it's a good question, right? Yeah. And that's actually quite regular. What you see here is, for instance, we start on the leaf level with Y, and then we go to A, B, C, right? And one reason why it's so complicated, and it's a little goofy that I do this example on t equals 3, is if you want to do that for general hash trees, right, then we don't have A, B, C, D. We run out of letters at some point, right? We can only have 26 letters. So now we do this general. So we actually already, if you understood that, you can start doing Instagram or whatever, right? So from now we generalize now, but there's nothing else happening here, right? So this stays the same, yeah.
If we assume that Oscar implemented an amendment attack or something and changed the very, very first original key public, would that mean that he would be able to change every parameter?
Yeah. So the question is if Oscar changes this key public, right? Yeah, I mean, then everything is lost. Then he could do his entire hash tree, which becomes Oscar hash tree. He can do whatever. Yeah. No, because we have not done the last lecture of this course. So you have to protect car public with what's called a certificate, which is a pain to do. Yeah. Okay. Now, the main thing is I wanted to show you. We're already done with the. We're not only done with the. Second one, you understood why they work. Yeah, your question.
Does Oscar know Y0 to Y?
No. Excellent question. We dealing with. This is a great. So he's saying. So Oscar or Bob? What? Oscar knows K-public, and then he said, these are K-public, right? We have two types of K-publics here, right? So, and this is normally, probably even last lecture, I have to look in the notes, we called that K-private and K-public. I dropped that. We have two types of public keys here. We have and this is maybe a nice word, we have the local public keys. This is X0 and Y0. There's the locals, again, winternets, right? These are winternets public key. Then we have this. So and that makes it messy. So we have a local, we have essentially 8 little public key schemes here, signature schemes, and then we put another one on top of that, right? So it's hierarchical. But excellent question. Good. So now we have to go to general MSS. So general Merkle signature schemes, exactly the same. And this is why it's great that apparently, unless you're lying to me, every single person understood more or less what we're doing here, right? The general case is exactly the same. There's nothing different, but it gets really messy once we drop our nice ABCD, right? Because now we need general variables and the indices are going to kill you, right? So, good. And that's probably why my beloved colleague said this is really difficult to teach, okay? Chapter 3, last chapter for today, MSS with general hash trees. Okay. So the main, for motivation, and this is actually good. At some point we want to write, we need an algorithm, right? We don't always want to do this big stupid drawings, right? We're running out of paper and chalk and whatever, right? So we need general names for that, and maybe this is a little bit to motivate that. So this tree, do people see that this is, not essentially, that this is a two-dimensional structure? we have kind of an X. X is bad because there's an X component and a Y component, right? Everybody with me here, right? So, and that's what we're going to do now. So we introduce a general name, node is the German word Knoten, right? Each of these, the A's, the B's, the C's, and the D's, they're called nodes, they're Knoten, right? So we have a general node name. We just talk about naming here at the moment, right? So this is, and we call them V. And we call them VI, and this is essentially the X component, right? This is going from left to right here. And then we need, because it's two-dimensional, we also need a Y component. No, I was wrong, of course I did. This is the I, this index is the row. I was totally wrong. I give you 100% the wrong answer, right? A wrong explanation. These are the rows, die Reihen, yeah? Right. What is a fancy word for, how do we call rows here in the Merkle signature tree thing? It's on the blackboard. What's the official name? It's not row, but level, right? This is, so row, Reihe zuerst, right? So row first. I've been doing that wrong for 35 years, right? Since I was a bachelor student. And this Y is and this is really in quotation marks, in Anführungsstrichen, because it's not, they're not really columns here. It's not a matrix, but this is going from left to right, okay? And it's a little messy because on level 0, we count from 0, 1, 2, 3, 4, 5, 6, up to 7. But on the next level, we're only counting from B0, B1, B2, B3. So here we count up to 8, up to 4, up to 2, up to 1, right? So because it's a, pyramid, right? Structure, okay? So an example here, very simple example is that we have, we would start here with V0, V0 of 0, and here we have V0, 1, right? And this would belong to X1, Y1. Example for t equal 1, I'm sorry, forgot that. And we go up one level, and here we would have, any ideas? What is the level here? What is the nice index to do, yeah? Exactly, V1. It's not complicated. You don't have to copy that. You see on the left-hand side, figure 12.6 in the book, right? You're welcome to copy, right? But yeah, okay. And these little things are what are normally the green bubbles are. So, what you see here, remember you told me, unless you were lying, you understood this here, right? This is a tree of degree 3. This is a degree of degree 3, right? You have all these V's there, right? All the nodes are not called A, B, C, D. Again, my co-author Tim Gunesi, Professor Gunesi, you're going to have him later. Who has worked with Professor Gunesi already? Yeah, he's great, right? So he said, you really want to do that, Christof, right? Call them ABC because we need this. And I said, yeah, let's do that. So it's the same more systematic way. I find when you start with it, it's harder to understand. Okay, so exactly the same thing. So, and the reason we cannot work with A, B, C, D here, we need this V00, V1, blah, 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 is now I'm going to show you algorithms how to compute that, right? We need later on, and if you implement that in a web browser, you can't do, we're looking here, we go one up, or B0 is missing, and red circles and green circles. Now we do a systematic way, and that's actually the last thing we're going to do today is giving you the algorithms. Okay, now we write. The first thing we have to do is we have to generate the tree. And there are essentially 3 steps. We compute the first leaf computation. And what are the leaves? The leaves is the bottom, right? These are the I equals 0, right? V0, the all V zeros, right? It's really stupid. I wanted to save paper, right? So I have to project, but these are also my notes, and now I'm going to cut that piece of paper in half. Again, I'm teaching for the first time. Next time, I'm not doing that anymore, right? Okay. So what we're computing here is all the leaves. That means we compute the public keys. Or this is not even leaf is. No, this is wrong. Leaves. This is WOTS computations. This is wrong. I'm sorry. So we're here. Do you see that? So we're doing these here. The leaves are one level up. So I'm below the leaves. I'm doing the X0, Y0, X1, Y1, blah, 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 blah. Put that next to it so everybody knows what Christof is talking about. So we do K private, comma I, K public, comma I, which we then call xi, yi, and I, of course, runs from 0 up to 2 to the t minus 1. Okay. If you want to put a remark in your notes, last week, right? So we're not how you do that. This really depends on your one-time signature scheme. In practice, it's actually often Winternitz, what we're doing here. Okay, so now we're here. Now we do the leaf layer, right? The leaf is I equals 0. Second, leaf computation, which is simple, right? We just do what it says here. So we do, no, it's actually not here. We doesn't say it here. We have to, we're doing this. We hash each of the public keys, right? So this is very simple for, writing down. So this is, I have to be careful, Y0 index J is the hash of all the public keys of Y index J. And here again, this time epsilon runs from 0 up to 2 to the t minus 1. Okay. So what we've done now, we did the very bottom, which is not really, it's not really part of the tree. The V's are part of the tree. And now we do all the other nodes, and there's a simple algorithm for that. It's not even, it's a formula. So this is, I call that the other nodes computation. Okay. Now we talk about V index I of J that means V1 here, the V2s and the V3s for this example, right? And we know, so we talk here, what we just did here, number 2 was A0, A1 up to A7. Now we have to do all the other ones. The construction principle is very, very easy. You always take 2 nodes from the previous level, right? And hash them together. So the formula looks a little bit messy, but it's, if you think about it, if you have this in mind, it's not that surprising. So this is essentially, this is now a longish expression. So you, what kind of index do we need here? Maybe that's a good question. If you're computing here, we're on level I, so what do we need? Yeah, exactly. So, and we need 2 of those, right? We start with 1 that are concatenated, right? And now here you do 2j, index 2j for the row index. It works out. And this is being concatenated with V also 1 level down, I minus 1. And the column index is 2j, 2j plus 1, Klammer zu. Is that right? Klammer zu, yeah. Okay, and what here we have to pay a little attention. I runs from 1 up to t. That means I always becomes smaller. This is because it's a tree, right? We always become smaller as we walk up our levels. And J potentially runs from 0 up to 2 to the t minus I here. Okay. And this is, you have to play with the algorithm. I'm not going to do that. Spend a lot of time doing that. I think this is really important. You understood, you're great, you're all smart. This is, I could have done, I think that's probably what another pedagogical approach, and once you're a professor for cryptography, you can choose what to do. You can also start with this and start filling the numbers in I and J. I think this is really messy, right? This is why I said, let's call it A, B, C, D. Everybody understands, this is not so complicated, this is kind of complicated. Yeah. Yeah. No, here?
Not in the exponent. Below.
Okay, I made a mistake. It's impossible. Good. Yeah. Any other questions? Yeah. Okay. So what I'm not walking you through this algorithm. Believe me, it works. Believe me, Julian is going to take care of you. Right? And now comes and this is not even that complicated. What is complicated now is how to deal with we have this fancy authentication path. Now I'm going to show you how to generate the authentication path. But again, I just give you the algorithm, right? This is something, and there's some, it's systematic, right? Okay. So this is computing the authentication path. This algorithm is in the book. You all have that as PDF. Some have that as hard copy, right? I'll talk a little bit about that, right? So the input is a Merkle tree. This is the tree generation here, right? So the input is what we have here, right? The nodes have this index vi, j. So this is what we, here are the leaves, here are the other nodes which we computed, right? This is the first bullet point, right? And now somebody asked about the index before, right? Now the index is really important, right? Now we talk about index C. C is, if I go back, You know, in this example, the index is either 0, 1, 2, 3, 4, 5, 6, up to 7, right? So you want to, before we said the first 3 have been burned, have been signed, we want to have the fourth one. The fourth one, right? So, okay, this is great here. I have a screen here that shows exactly the same picture that you see. This is fantastic. So C, right? C is a value, and you see that here, C is a value that runs from 0 up to t minus 1, right? So it's, yeah. And again, in practice, remember here. In practice, you choose t equals 20. So that's a tree that has 1 million leaves, right? It's homework for next week, right? I'm kidding, it's not homework, right? You can imagine a really big tree, right? Then the index C runs from 1, 2, 3, 4 up to roughly 1 million, right? The output is this authentication path. This is what we saw here. Has one member from each level, right? One A value, one B value, one C level, right? And that's the algorithm, right? You run from 0 up to t minus 1. You have to compute this auxiliary value Q. Do you know what these things are? This Rundung, the fancy terms are called floor function, right? Because if you divide C by 2 to the I, normally you get a krummer Zahl, right? You get a fraction out. You don't get 5 out, you get 5.37 out or something, right? And this is abrunden, right? Rounding down. This is the floor function. This also exists this way, and that's the ceiling function, right? This is abrunden, right? Round down. And here you can compute the sibling node here at this point, right? Which means this R value here, and this becomes the authentication node on the level, right? And the levels run from 0, 1, 2, 3, 4, 5 up to t minus 1. And this gives you one A value, and you do that for every level, which is, where was it here? I think we saw that, right? You know, the authentication path, which is the red one, right? There was one coming from level 0, one coming from level 1, one coming from level 2, right? So on every level, you need exactly one value, which is this A here, right? Again, if you do one by hand, and actually, of course, it's in the book. So if you run the algorithm that I just showed you, the algorithm gives you here A0, V02, right? V02. This is V10 and V21, which is exactly the red ones here. Do you see that? Yeah. How frustrating is it for you that I don't talk more about this here? Can people live with that you do that in your homework assignment? Yeah, we'll see. Okay. It works. This is what, I use this algorithm, and surprise, surprise, you get exactly this out. You also get it for t equals 20, right? You have 1 million leaves, and then you don't have 3 steps. You have 0, 1, 2, 3, 4, 5, up to 19. You have 19 steps. It always gives you the right nodes that you need, that you put in the authentication path. Okay. One final remark. So we're done with 3, but I just want to do for the very end of today. See, actually, you can go to sleep. So what I'm saying now is not important for the exam but important for life, right? If you want to stay in security. So this is comments. Colon, Doppelpunkt, MSS in practice. one is MSS is stateful. Julian, did you already talk about state last week or not? But we do it now, right? I think that's one example. Stateful is a very fancy zustandsreiche, zustandsvoll. What that means is you have to keep track of things, right? And in particular, we had that here. You see the check marks. Alice have to keep track what she has used already. This is not pretty, right? So because, for instance, if there's some kind of database or some kind of memory, you have said, if Oscar manages to erase this check mark here and Alice start to reusing it, that becomes weak, right? So it's not something that we want to have, but we can deal with this, right? So it's stateful. This is I like here, okay. MSS uses hash functions. And in practice, this is very often SHA-2 or SHA-3. For 3 tasks. And this is a little bit confusing. And when I wrote the lecture notes, when I wrote the book, I said, oh, really? This is interesting. Namely, we make a little bit a layered system, right? So originally, which you don't see here, the hash function, right? I don't know. Oh, we did hash function a few weeks ago, right? What was the motivation? How do you remember the motivation? What was the motivation for using hash function? Which context was that? Do you remember? Signatures, right? There was a thing, we did RSA signature and said, oh, great, now we can sign messages with 2,000 bits, right? Which is, 128 characters. This is stupid, right? We want to sign PDFs. And then we said we need hash functions for signing. The same here, right? If you want to sign a PDF file, 1 megabyte, right? 8 million bits long. With the internet, the first thing you have to hash. So M is the hash version. I just call that message here, right? So this is like 3 weeks ago. I think it was 444. That's the lecture, right? That's how we look in the book, right? Watch the video, right? It's video number 20 or so, right? Then we need it for Winternet's one-time signature scheme. This is what we did last week, right? And this is very, this we have to hash 2 to the W minus 1 times, right? So here we computed in our notation, right? We computed signature xi of m. So this was really last lecture. It was 2 weeks ago because it was public holiday. So this is the first time we need a hash function. This is the second time we need a hash function. And then the third time. This is today. Merkle signature scheme hash tree. This is today. Lesson learned, hash functions are important in cryptography, right? You need them all the time. Right, so. Good. In the final remark, this is just very brief, is there are generalizations of MSS with multiple hash trees. Yeah, so to speak, you have hash trees of hash trees, right? Which we are not going to do here. Gut. almost in time. Any questions? If not, ping me, ask Julian during the various help sessions. Exercise was really fun. I have not taught in 6 years. It's really, really totally fun with you. You're great students. Oh, there's a question. Yeah.
One general question.
Yeah.
Regarding quantum computing. Are those post-quantum, are they already being standardized?
You mean being used or? Yeah. So his question is a general. Yeah.
Because of the targets now decrypt later.
Oh, yeah. This actually, I didn't mention that last week. This is a good question. He said, why are we using PQC schemes now? And I don't think I talked about it, right? There's this notion which I talk about in the book is called store now, decrypt later, right? So one argument is, why should we worry about it? Because I made a big spiel about it. Maybe we see them in 10 years, maybe in 20 years, maybe never, right? And the very smart physicists around say, good luck, this is never going to work, right? I don't know. I can't predict the future, right? But the big argument is why, but right now hell is loose, right? Die Hölle is loose worldwide because people push them into web browsers, they push them in WhatsApp, they push them literally in BMWs, right? In cars. So why is that? There is this, and we know that from, among others, from the Edward Snowden documents, there's this store now, decrypt later. We know the big intelligence agencies doing that. So they're recording big powerful countries, England, US, probably China, probably Russia, maybe Germany, I don't know. They're storing a lot of internet traffic, and we know from the Snowden papers, in particular encrypted internet traffics, right? So they have these halls full of hard disk, right? They're storing that. And right now they can't decrypt because they cannot break RSA, they cannot break ECDSA, right? They cannot break Diffie-Hellman. Should in 20 years or in 10 years quantum computer be available, they can go back, look in their hard disk, and then break that stuff, right? So this is called store now, decrypt later. And we know from Snowden, at least NSA, one example, National Security Agency in the US, is doing that. And that is the reason we don't want to take the risk that the physicists don't succeed with building quantum computing. We're scared that might happen, and that's why we have to switch already. Excellent question, good final question. Thank you so much.